So the aim of the first lecture is to give you a bit of a view on what algebraic geometry is. So at a high level, algebraic geometry is the study of curves and surfaces and other higher dimensional objects. Defined by polynomial equations. I'll make this more precise in a few moments and define an affine variety, which is not all the objects we might care about in algebraic geometry, but it's what we'll talk about mainly in this course, and that's what I mean by higher dimensional objects defined by polynomial equations. One of the reasons algebraic geometry is an important area of modern mathematics, in the sense not only that it has interesting theorems, but it sort of extends its tendrils into everything, including physics. The reason for that is hard to summarize, I think. For example, algebraic geometry has some purpose in statistical learning theory, as the SLT seminar here will attest. It's not easy to explain why in a few sentences, but one of the deep phenomena in algebraic geometry that perhaps explains its prevalence in other parts of mathematics is that it's the home of one of the most important dualities say home. I guess various branches of mathematics can fight over this a bit, but geometers win. And that duality is spaces versus functions. The duality between space and functions comes down ultimately to the fact that although we feel like we're embedded in space, we sort of only infer the existence of space through making measurements or observing signals. But you could put as the primal thing a space. I'll just write X. You could say that's the space you're sitting in. Or you could say, no, the real primal thing are functions on that space. And it's not clear that either of them is really true. They're dual. Let me give a bit of a list, at the end of which I'll put geometry and algebra. So geometry is the study ultimately of space, of spaces meaning things like curves and surfaces and such things. But the way we study them is often algebraic. And the interplay between these two points of view is what makes algebraic geometry so beautiful. So although curves and surfaces are sets of points, if you like, with some structure, a topology, although we won't get to that in this course, day to day, geometers are spending more time manipulating polynomials on pieces of paper than they are looking at pictures of things. And polynomials and ideals, which are collections of polynomials, are the way we do that. Maybe I'll add one more entry to this table, which is, in some sense, one of the interesting aspects of this course, in the sense that it emphasizes it early. There's a kind of computational view on what geometry is about, which comes from looking at the computational content of the manipulations you do to these objects, polynomials, ideals, and so on. We'll talk a lot about that. We're going to discuss Grosvenor-Basie's, Buchberger's algorithm, and a kind of quite effective view on some of the basics in algebraic geometry. And that will give you a pretty good feel for the computational content of the right-hand side here. Now what that means geometrically is actually in some sense an open question, so maybe that's an interesting thing to ponder as we go forward. Okay. An administrative note, if you're using the teleport button to get back to the orb, maybe leave off. That gets in the way of the orb cam. Sorry about that, that's a bug, my fault. So a technical note, references I'm going to write to CLO, to the textbook, will be things that look like lemma CLO 1.2.3. I don't need to explain what CLO means. This means chapter, section, and what CLO writes as lemma 3. So throughout the course there's going to be references both to lemmas, propositions, and so on inside the textbook, but there will also be lemmas and so on in, say, the notes that I'm reading from right now, and those will just get references without this CLO prefix. Hopefully that'll be clear as we go on. So, to explain polynomials, I need to first start with coordinate functions. So from a very early age, we're introduced to the idea of space being imbued with a coordinate system, and we learn to associate the letters x, y, and z to the axes for that coordinate system. But what does it mean to stick a letter on an axis anyway, right? That's some convention we're used to. I want to emphasize that these letters are coordinate functions. So the way to think about these letters is that they are gadgets, functions, that extract coordinates from points. Okay, so if that's a coordinate labeled x, then x of p is 3. Now, you used to being able to think about x, y, and z in several slightly different ways, right? But I want to sort of zoom in on that and disambiguate them. So to start with, the letters x, y, and z will stand for me for coordinate functions in this sense, acting on three-dimensional space. Just a moment. When we say that the equation of a circle is xy squared, x squared plus y squared equals 1. What we mean is that the following procedure produces what we call a circle. If you take every point P and test it according to the following test, that is, you apply x to P to get a real number. So at the moment it's not supposed to be clear what kind of gadget that is anyway, right? That expression on the page. It's an equation involving some things, polynomials, but we're going to be very careful about defining polynomials in a moment. So the way you actually use that description of the circle is that you test the point P by evaluating x on P to get a real number. You square that real number. You evaluate y on P to get a real number. You square it, you add it to xp squared, and then you compare it to 1. If the test is passed, then P is in the circle and otherwise not. I know you've all seen polynomials. That doesn't mean you know what they are. So what kind of thing is this x squared plus y squared minus 1? The thing that if we test it and it's equal to 0, we get the circle. Well, we could say it's a function. So when I say this thing, I mean kind of what does this expression on the page, this combination of squiggles, denote, mathematically speaking? Maybe without the question mark. I don't know what it denotes with the question mark. We could say it's the function that sends p, a point in the plane, say, to xp squared plus yp squared plus minus 1. That would be a function from the plane to real numbers. That can't be quite right, because if I think about the following expression, that also computes the same function, right? If I plug in a point p, I'll get out the same output. Yeah, now I think about it, this is not such a great example. In fact, we'll prove in a little bit that I can't really come up with a great example. But I want to belabor this point anyway. However, I want to distinguish between that function and the rule that I've written down to compute that function. Because a function is strictly speaking not a rule, it's just the input-output pairs. Okay, so a function is just the set of input-output pairs determined by whatever procedure you've given for assigning outputs to inputs. Many different rules can determine the same function. For example, Ken was talking last time about merge sort. There are many other sorting algorithms that, given the same list, would produce the same output. But we distinguish the algorithms or the rules even though they compute the same function. They may have different properties. So, in some sense, the distinction between the rule that computes this polynomial function and the polynomial is more subtle than that, as we'll see. You don't have to make this distinction, but I'm going to here. So the function it's not really correct to think about this as just being a function. It's more like a rule, but what kind of rule? Alright, so the expression x squared plus y squared minus 1 is more like a rule for computing this function. Or an algorithm. Okay. So a polynomial, which is the name for this particular kind of rule, computes numbers from other numbers. and determines a function, but is not synonymous with that function. All right, some examples. And then I'll give an actual definition. So I'm going to write down two polynomials, one in one variable, x, and another in two variables, x and y. The second may be less familiar, but I think you've all seen both. All right, so it doesn't cause you any consternation for me to write those things down. You know what to do with it. You'd even busily start sketching the first thing, for example. But what is this thing I write down on the page? You know, you might say it's a formal expression, which is kind of just a way of avoiding the question. Well, let's have a look at the information that's contained in that description and try and see what we think is really going on. So the information on the left-hand side, if you like, is, well, first let me write this as plus minus 2 times 1. So I can recognize here powers of x, right? This is x to the 0, this is x to the 1, this is x squared. And hanging off those powers of x are coefficients, minus 2, 3, and 2. So the information here, what's in common to any polynomial in the variable x are these powers of x. But what may differ are the coefficients. So here the coefficient of, let me put 0. That stands for x to the 0. The coefficient of x to the 0 is minus 2. It's 1, 2. Coefficient of 1 is 3. The coefficient of 2 is 2. Coefficient of x squared, rather. And I could continue and just put zeros everywhere. Okay, so that table there is an equivalent description of that polynomial. And in fact, I'll argue in a moment, is the polynomial. On the left-hand side is some other way of presenting that same data. Okay, what about this case down here? Well, this involves a few new features. Obviously, there's two variables involved. So first, let's write this as x to the 0, y to the 0. X squared is really x squared y to the 0. That's really x to the 0, y to the 2. And this is, well, x squared y to the 1. So here, what I wrote in this table were the powers of x, right? So now I've got not a power, but two powers. So I write a pair of numbers. And you might say, well, who says x goes first? Right, as you can see here, I wrote 2, 1, right? So I could have written that 1, 2 if somehow y were to be preferred to x. I guess x comes first in the alphabet, so it's natural to do that. In the sense you weren't worried about it, probably. But when we're mapping, well, it's a hint that variables come with an ordering. Okay, and we'll come back to this in many guises later. Okay, but continuing with the assignment of coefficients to these pairs of exponents, 0, 0 has coefficient 1, that's that there. 0, 2, that was this guy here, has coefficient 1. 2, 0 here has coefficient 2. 2, 1 has coefficient 3. And then there's lots more pairs and they all get 0. Okay, so a polynomial is this assignment of coefficients to monomials. And a general monomial would be something like a bunch of powers of x. So for example, x squared y to the 1 or x to the 10 y squared in two variables and so on. If you tell me what the coefficient is of every one of those, you've specified a polynomial. All right, so I'm going to make a more formal definition in a moment, but is there any question at this point?
Yeah, kind of, right. So we want this assignment to be finite, I guess, or finitely many non-zero.
Correct. Yeah, that's right. So
otherwise, so it's kind of a slight funky special case, right?
it's not just a function, right? Yeah. So I should I should say an assignment. Not all assignments of coefficients to monomials will satisfy the rule that I'll write down in a second for being a polynomial. But the rule is simply, as Eleanor said, that only finitely many of these monomials, represented either by writing this expression as here or just reading off the powers, so really this monomial here would correspond to this tuple. Only finitely many of those tuples can be assigned a non-zero coefficient, which means, if you like, that if you choose some ordering for them, eventually there's all zeros. Yep. Any other questions? Okay, if not, let's migrate to the next set of boards. Just clearing the boards, feel free to ask a question. Okay. Before I give the formal definition of polynomials, I need to say at least remind you the word field. So field, well, I'm not going to define a field. So you can check the textbook for the proper definition. We're going to work just with Q, R, and C, so I don't need to give a full definition. So maybe I'll say it like this. Let K be a field. And if you don't know what the definition of a field is, that's okay. Just anytime I say let K be a field, you can just read either Q, R, or C. And what's in common about these, and what I'll need, is that you can add and multiply any two elements of these collections. That's rational numbers, real numbers, and complex numbers. And you can divide or multiply by the inverse of any non-zero number. That's a field. And recall that the natural numbers has 0 in it, damn it. Okay. Then, a polynomial in n variables with coefficients in k is an assignment this is a bit awkward, but I don't want to undo all that. F is the name of my polynomial, is an assignment of coefficients. Those are things that live in the field tuple alpha, which is an n tuple of non-negative integers, with only finitely many coefficients non-zero. Okay, so for every tuple, there's n variables. An n variable polynomial is the data of, for every tuple of n non-negative integers, some scalar, some element of the field, which is meant to be interpreted as the coefficient of that monomial. But here you see there's no letters, there's no x1, there's no xn, there's no xyz. It's just an assignment of coefficients to these tuples of non-negative integers. That's admittedly a bit abstract, so let's start decorating it to make it look more familiar. So we can consider first of all the polynomial, the assignment of coefficients, that assigns 1 to exactly one of these tuples and 0 to everything else. So given alpha, we denote by x to the alpha. This is just a formal notation. X doesn't mean anything, it's just a formal symbol. Really the information here is just alpha. The polynomial which assigns coefficient 1 to alpha and 0 to all other tuples. And really secretly you think of this as being 1 dot x to the alpha, right? So x squared or y squared or x squared y is the kind of thing that is supposed to be in your mind right now. Addition and multiplication of polynomials. For most of the course we won't need to worry about these kinds of details, we'll just use polynomials and manipulate them in the usual fashion, but at least once you should see what these things really are, because otherwise it'll bug some of you for the whole time. So given polynomials f and g, in the above sense, f plus g is another polynomial. To tell you a polynomial, I just have to tell you the coefficients it associates to every alpha. Oh, maybe I should have said, in case you're not familiar with this notation, so superscript n just means this is n tuples of natural numbers. The coefficient that f plus g assigns to alpha is whatever coefficient f assigned to it plus whatever coefficient g assigned to it. And this addition here is taking place in k, right? So we know what that means. The product is more involved and I'm not going to say much about it. But I encourage you to do the exercise that's mentioned in the text, which asks you to check that with this rule, for example, what does it ask you to check about multiplication? Right. It asks you to check that x to the alpha times x to the beta is x to the alpha plus beta. And you also want to check that multiplication distributes over addition. Those two things together mean you can multiply polynomials in the way you're used to once we have an expression that makes sense. Okay, so the formula is you sum over all beta and alpha pairs of n tuples whose sum is alpha. The sum of pairs, sum of tuples is done coordinate-wise. So you add each element of the tuple to the corresponding element. and you multiply the coefficient that f assigns to beta by the coefficient that g assigns to gamma, and then you add them. And finally, to multiply a polynomial by a scalar, the coefficient that it assigns to alpha is lambda, which is an element of the field, times the coefficient f assigned to alpha. That's it. Those are the operations on polynomials. Two polynomials f, g are equal if they assign the same coefficients to the same tuples. Okay. That's not meant to feel like a very familiar or comfortable view on what a polynomial is, but it has the virtue of being precise. Now, we're not going to run around and express polynomials by talking about this assignment of coefficients to monomials all the time. We want a more compact notation for that, and that compact notation is the familiar notation. Sorry for giving you vertigo there if you're in orb camp. Okay, so let's now start introducing more comfortable notation for this. Given variable names, say x1 up to xn, I can define a polynomial associated to those names, so say xi, to be x to the ei, where ei is the tuple that has a single 1 in position I. So that's the polynomial which assigns the coefficient so ei is a tuple of non-negative integers. Right, so if I was to go back to my tables from that example, x to the ei, or xi, would be the polynomial that puts a single coefficient on this column of 1 and zeros everywhere else, right? So it looks like 1 dot x to the ei, right? Okay. And given an element of the field, we think about it as a polynomial which is lambda times, well, sorry, I should define 1 first. So the polynomial 1 is x to the 0. That is, it's the function that assigns 1 to that 0 tuple and 0 to everything else. If lambda is in K, we also write lambda for the polynomial, which is lambda times 1, using that third row of the previous board. Right? So that would be the assignment of the coefficient lambda to the tuple 0 and 0 to everything else. Okay. Now, let's start putting this together and getting ourselves back to what we thought we understood already. So check the following things. X to the alpha, which I defined as a polynomial, is equal as a polynomial to the x1 to the alpha 1 times x2 to the alpha 2 all the way up to xn to the alpha n. Where f to the n for a polynomial f and integer n means 1 if n is 0. I guess n is a bad choice, right? So I've defined how to multiply things. So that means that I give you an integer m. If m is 0, just say f to the 0 means 1, 1 being this polynomial, right, the polynomial 1. Otherwise, multiply f with itself m times. x1 means this polynomial. I can multiply it by itself alpha 1 times, right? Here, alpha is the tuple alpha 1 dot 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 alpha n. Okay, so the right-hand side here is multiplication of polynomials, and this is that notation I introduced earlier. So check that this x to the alpha thing is just this product of powers of xi as polynomials. I already mentioned the second part, which is to check that multiplication of these things, you could deduce that from the first part if you like, or directly. And finally, if I have distinct tuples of indices or exponents, and then I take some coefficients, multiply them, then check that's the polynomial which has coefficient of alpha I being ai. Okay, all that together means that we can basically work with these polynomials by writing them in the usual way. And then we can actually start doing things with them. Okay, so I've just defined the set of polynomials. The set of polynomials in n variables in the above sense, right? Polynomial is a function assigning to tuples of non-negative integers coefficients, and the n there is the power of the natural numbers, that is the length of those tuples. I could denote that by Pn, or if we have names x1 through xn, an ordered list in mind, we write k square bracket x1 through xn. Note that the definition of the set of polynomials didn't involve these names at all, which might be a bit strange. So in some sense, kxy is literally the same thing as kuv. There's no set theoretic difference, but that's neither here nor there. So I'll just say a few things about that. The set of polynomials is what's called a commutative ring, which just means that you can add and multiply polynomials in a way that satisfies kind of the laws you'd expect from integers. In particular, multiplication distributes over addition, and addition, it doesn't matter what order you do it. Multiplication, it doesn't matter what order you do it. And both of them are associative. So let's give some examples. Well, we've already seen a bunch. x squared plus y squared minus 1 is a polynomial. Now you could read this expression either as being the instructions to send 2, 0, to associate that to the coefficient 1, 0, 2 to associate that to the coefficient 1, and 0, 0 to associate that to the coefficient minus 1. Or you could view this as literally doing algebra inside this polynomial ring. I'm going to repeat this term, so I'll just mark it here. We'll call this the polynomial ring. You don't need to know what a ring is. We're only going to use polynomials, but that's just the standard term. So you could also read this expression as being literally operations in the polynomial ring, right? You can take x squared, that's a polynomial. You can take y squared, that's a polynomial. You can take minus 1, and then you can add them. So either way is available to you in terms of thinking about what the underlying data structure here is. Maybe I don't need to stress all of these. There's more examples in the text, but for the sake of time I'll just write down one more. I think it's the one from earlier. Perhaps not. Okay, there's more examples there. One I do want to highlight is that this is not a polynomial. It was important in the definition that only finitely many tuples got assigned a non-zero coefficient, but the assignment of coefficients to powers here would be something like 0 goes to 1, 1, that is x, gets assigned the coefficient 1, 2 gets the coefficient 1, and so on. Every non-zero, every power gets assigned 1, and that's not finitely many non-zero coefficients. So that is a function, but it's not something that lives in the polynomial ring. Okay, any questions about definitions?
Yeah, but it's a complicated one, so I'll wait till later.
Sure. Well, while you're thinking about it, if you have any questions, let's migrate over to the next set of boards. Were there any other questions? Okay. So let's start actually proving some things. Okay, if f is a polynomial, and I denote by capital lambda those tuples which get a non-zero coefficient according to f, then I claim f is equal to this more familiar looking gadget, which is a sum of linear combinations of powers of x. This expression here, you should interpret this sum as being the sum in the polynomial ring, this as being multiplication by a scalar, and this is this particular polynomial we defined earlier. Once we have this expression, we never have to think about f as assigning coefficients to tuples anymore. We just work with this more familiar thing. All right, and this is a nice little calculation that checks you understand the definitions. Well, what does it mean for two polynomials to be equal? It means they have the same coefficients for every tuple. So to prove that equality, I need to just compute the coefficient assigned by the right-hand side to any beta. Okay, but how does the definition of addition of polynomials work? The coefficient of a sum is the sum of the coefficients. Strictly speaking, I'm doing an induction here, but you know, give me a break. So that's a sum of alpha of those coefficients, and by definition, if you multiply a polynomial by a scalar, the coefficient comes out the front. And what is the coefficient that x to the alpha assigns to some beta? Well, it's 1 if alpha is equal to beta, and 0 otherwise. So this is notation that'll probably come up a few times. It's called the Chronica Delta. So the Chronica Delta is 1 if the condition in the subscript is true, and 0 otherwise. So what happens if you sum over a bunch of things and you multiply by 0 unless that thing is equal to beta? Well, you just pick up a contribution from a beta. But that means this polynomial assigns to beta the same coefficient. Excuse me. The same coefficient that f does. Okay, so hence f is equal to sum over alpha, a alpha x to the alpha. Any questions about that? Okay, so given a tuple alpha, we define the weight or the total degree of alpha, denoted with these vertical bars, to be the sum of all those non-negative integers.
I think you cut out like briefly then. Like you came back in when you said something about vertical bar.
Oh, really? Okay. Yeah, I suppose it could be an internet
Should we be
issue on
confident
mine.
that
Sorry?
is whatever you said in the recording?
Yeah, it'll be in the recording, that's right.
Okay, maybe we just press on.
Yeah, I guess there's not a lot I can do about it, probably. Okay, so
Just watch out for us like rushing.
yeah, I guess somebody was writing on the board in order to let me know, and I was like, "Screw you, get off my board." But they
Yeah, sorry, Dan, that was me. I was doing my best.
I was just
Sorry.
thinking, very hard. It's very hard to break through my my zone of concentration.
As someone who's lectured more, I understand.
Yeah. I'm just given how many people over the months have come up and scribble on boards, I have a reflex of just like erasing. Okay, so given a polynomial f, which we know now we can write as a linear combination of these x to the alphas, which remember if we give names to the variables is just this monomial. I guess I haven't used this term before. I intended to, but this is called a monomial. This is a very important term. So a monomial means one of these x to the alphas, a polynomial which just has powers of x and just one term in it. When we add linear combinations of monomials, any monomial with a non-zero coefficient in f, we call that a term. And that's a familiar term. If you write x squared plus y squared plus 1, referring to the summands as terms is hopefully familiar to you. And if the polynomial f is non-zero, we call the total degree of f is you take all the alphas, all the terms, that is all the alphas where the coefficient is non-zero, take their total degree and take the largest one. Okay, those are integers, there's the largest one, there's finitely many. That's the total degree. Beware. Okay, so polynomials in multiple variables, like this one, don't have a degree in the same sense that single variable polynomials do. You can't, it isn't obvious how to order these terms. So for example, if I say x squared y plus xy squared, which one is first? Well, they have the same total degree in the sense, right? They both have 3 if you add 2 and 1, and they both have sort of degree 3. Which one should sort of go first? Well, it's not clear. All right, so those are polynomials as finite data structures. The next thing that I want to do is to introduce the associated function. I can hear some sound. Maybe everybody can make sure that they're muted. I don't know if it is a number of, like the number of people who it's trying to process the voice of, but it's possible that might help. Okay, so the associated, so given a polynomial f, the associated function capital F, which goes from Kn to K, is the following. Well, given any polynomial, we know we can write it in this form. And the function takes a tuple C of scalars and just kind of reads those coefficients as an instruction for combining products of powers of those scalars. So the right-hand side here takes place entirely in K. Right, it's just multiplying and adding scalars. So from any polynomial, we get a function in this fashion. Now that function is to be distinguished from lowercase f. This function, since it's the set of all input-output pairs, is an infinite set as soon as k is an infinite field, whereas f, lowercase f, is always a finite data structure. Right? Now note there's a potential for confusion between lowercase f and uppercase f. So if f and g are polynomials, then I'll write f equals g means equality as polynomials, that is, they have the same coefficients. Capital F equals capital G being the function associated to lowercase g, means equality as functions, that is, they have the same output for every possible input. Well, clearly, if you look at this formula here, if f equals g, I mean, if they're the same polynomial, of course the associated functions are the same. So clearly, if f equals g, then capital F equals capital G. The converse is also true. It's not difficult, but it's also not obvious immediately. Converse is also true if k is infinite. I say it's not obvious because it's false if k is finite. Okay, so hence we often elide the difference between f and capital F. So we often conflate a polynomial with a function, and that's completely safe as long as the field is infinite. Elide, skate over. Okay, that converse is what we're now about to prove. And that will be kind of the main piece of work in this lecture. So this is a proposition from the text. So it's proposition 5 of section 1 of chapter 1. And it says the following. Let K be an infinite field. And F a polynomial. Actually, that's fine. So if you're thinking of field as just meaning Q, R, or C, those are all infinite. So this is true for those. And take a polynomial f, and let the function it computes be capital F. Then the polynomial is 0 if and only if the zero polynomial being the polynomial with 0 coefficient for everything, if and only if the function is 0, meaning the function that sends every input to 0. Okay, proof. If you're not familiar with this term if and only if, P if and only if Q, P and Q being statements, means P implies Q and Q implies P. This direction is sometimes called the converse. And the other is sometimes called the forward direction. I guess if I call this the forward direction, I should call Q implies P the reverse direction, but I'm not going to do that. Well, one direction is clear. It's clear if F is 0, then capital F is 0. For the converse, yeah, that may be the reason. Or maybe the sneaker company is full of mathematicians. That seems more likely. So for the converse, suppose we proceed by induction on n. N being the number of variables in the polynomial ring. The base case is n equals 1. So to be clear, the statement we're proving by induction is that in a polynomial ring with n variables, if the function determined by a polynomial is 0, then the polynomial is 0. Right? So that's f equals 0 implies f equals 0. That's the statement we're proving. Let's do the base case. If n equals 1, we know, and we'll revisit later, and maybe it'd be interesting if you could try and recall the proof or figure it out in the exercise session perhaps. But recall that it's quite easy to see that in the single variable case, if you have a polynomial of degree m, then it has at most m roots. Okay. So if you have a polynomial of degree m, and every polynomial that's non-zero has some degree, so let's maybe put it like that. So if f is a non-zero polynomial and it has degree m, and it determines the 0 function, well, that means it has everything in K as a root. And since K is infinite, it has more than m elements. This is a contradiction because you've deduced that f has more than m roots, but you also know that it has at most m roots. Okay, so hence, well, this doesn't work as soon as f has, so the contradiction here is with the hypothesis that f is non-zero, right? So f has to be 0. So as soon as capital F is 0, we know lowercase f has to be 0 for degree reasons. Okay, so that's the base case. We're going to proceed around the back for the next step of the proof. Any questions? How's the audio?
Yeah, audio's good. You can use the back of the board here.
Yeah, I put some boards
It's
on the
good.
back.
Nice.
Audio's all good.
Okay, cool.
Cool.
All right, so let's do the inductive step. So suppose the statement that converse holds for all degrees less than or equal to capital N. And let f be a polynomial in n plus 1 variables. We're going to suppose that the function associated to it is 0 and prove that f has to be 0. Well, we can collect terms to write our lowercase f as okay, so what's going on here is that there's an exercise that asks you to think about this, but what I'm doing here is doing something like taking x squared y plus xy squared, and I'm saying, okay, the last variable is y, so I'm going to think about that as a polynomial in y with coefficients which are polynomials in x, right? And maybe I need to group terms, so suppose that was x squared y plus x cubed y. Well, then I would think about it as x squared plus x cubed y. And this thing here would be one of these g's in that case. Okay, so it's pretty clear that you can collect terms in this way, and I'll just take that for granted. Okay, so we think about f as being a polynomial in the final variable, xn plus 1, with coefficients in the earlier ones. So where these gi's are polynomials in x1 through xn. Now, for any tuple C, we can construct the following polynomial. Which is h sub c, which is evaluate f, that is substitute xi equals ci up to cn, but leave that final variable unchanged, or just to be clear about it, so that's evaluating gi on c and leaving that final variable as a variable. So that's a polynomial in the polynomial ring in one variable. Now since f equals 0, no matter what you substitute for that last variable, no matter what element of the field you put in there, you have to get 0. That's what f equals 0 means. But that means that the function associated to h sub c is 0. I'll just write that as capital HC. Okay, so that's the function associated to that polynomial. Well, by the n equals 1 case, we know that that polynomial must be 0. But then, well, what does that mean? That polynomial being 0 means all its coefficients are 0, but the coefficients are these GIs. Now, the way this worked, we fixed this. So we picked a C, and then we've deduced that this polynomial h sub c is 0, and therefore all of its coefficients are 0. But this C was arbitrary, right? So we've now proven that GI of C is 0 for all I and for all C. But that means that GI is the 0 function for for I between 0 and m, where GI is the function associated to G little gi. But those are polynomials. The GIs are polynomials in fewer variables, in n variables. So by the inductive hypothesis, we have that GI is 0 as a polynomial, and then if you examine the expression for f again, we must have f is 0. So that's it. A corollary, the thing I stated earlier, I'll just be a bit abbreviated. If f, g are polynomials, then they're equal as polynomials if and only if they're equal as functions. What am I missing? The statement's false as stated. Why?
Something about the field.
Yeah, right, if k is infinite. If you're struggling to think about what goes wrong in the finite case, you might like to think about that. Okay, so as long as we deal with infinite fields, functions, polynomials are the same if and only if they determine the same functions. Okay, so we've got about 10 minutes left. I'm going to define affine varieties. I might not have time to talk about parameterizations, but well, we'll see. Are there any questions? We're done with defining polynomials. This is it for basics of polynomials now. Okay then. So, affine varieties. These are the basic objects of algebraic geometry. So I said algebraic geometry was the study of curves and surfaces and other higher dimensional objects defined by systems of polynomial equations. So given a field K, we're going to write ANK, or just A to the N, for K to the N, just meaning tuples of n tuples of elements of the field. The reason to introduce this A for affine, is, as Ken pointed out somewhat earlier, I think it was last time, we want to think about this as having geometric structure rather than being a vector space or something like that. Okay, this probably won't come up for a while, so it'll just be notation, but there's some reason for it. And we call this n-dimensional affine space. N equals 0 is allowed, but we're not going to worry about that here. Might like to think about what that would mean. Okay, so definition. Let's take some polynomials. This is my system of polynomial equations. the set of simultaneous solutions of all of those equations will be denoted by this blackboard bold V. So that means all the A's in AN such that it's a simultaneous zero of all of those equations. Now, what do I really mean by this? This means really capital F1, right? F1 is a polynomial, but I can evaluate it on a tuple that is a point of Kn in the way I described a few boards ago. So at this point we're going to start ignoring the distinction between polynomials and functions when it comes at least to evaluating them. If I say evaluate a polynomial at a point, say A underline, then I mean evaluate the associated function there. I don't think that will cause confusion. Okay. This is the affine variety. That's the name for such a thing, determined by the polynomials f1 through fs. Notice that this only depends on the set f1 through fs. It doesn't depend on the order, even though there's a kind of order appearing here implicitly. This set of S equations, maybe I should make this clear that this is really S equations. So all of them have to be true for a point A to be in the set. There's no order there. Okay. For the moment, we only allow finite systems of equations, f1 through fs. You might ask, well, what about if I have infinitely many equations? What kind of thing is that? We will answer this very satisfactorily with the Hilbert basis theorem in a few weeks. But for the moment, we only consider finite systems. I'll also remark, as has been discussed on Discord, that the conventions around the word variety differ a little, so some references wouldn't call this a variety. They would insist on something called irreducibility as well, but we're going to follow the text here, even though I guess outside the context of this course I would probably insist on irreducibility myself, but we'll follow the text. Okay, some examples. If f is 0, well, we're looking at the points where the zero polynomial evaluates to 0, and that's everything. So the whole space is an affine variety. At the moment, an affine variety is just a set. Later on in your algebraic geometry journey, you'll think about it as a more complicated object, like a ringed space, for example, but here it's just going to be a set. Now, if I take f to be 1, since 0 is not the same thing as 1 in my field, if I ask what are the points where that polynomial evaluates to 0, there's nothing in there. So the empty set is also a perfectly fine affine variety. I think I want to, there's a lemma in my notes saying that finite unions and intersections of affine varieties are affine. I think I'm going to state that and leave that as an exercise to you to take a look. So if these are affine varieties, so too are the union and the intersection. That is, you can find a system of polynomial equations that cut them out. But I do at least want to introduce the object that you may have seen around the back of these boards, which is a particular case of an affine variety. It's a surface, and we're going to spend some time thinking and talking about it. So maybe I'm going to move over to the next set of boards, and on the way maybe you can take a peek around the corner and see that object over there. How should I do this? No can collide, no. I could do it on a personal board, I guess, so we're close to this object. Let me see how much I have to say. Yeah, maybe that's okay. So, yeah, given the time, maybe I'll just erase this board and we'll put it up here. Okay, so I'm going to write down the defining equation for this surface. Example. You might ask, what does this word surface mean? Well, it has a technical meaning. It means something of dimension 2, but I haven't defined dimension properly, right? It's not so easy, actually, to decide what the dimension of something is, just given the equations that define it. But let V be the set of solutions of this single equation. So the set of points where evaluating this on x, y, z gives you 0. And I'll call this F. Okay, so that lives in A3, right? Because there's 3 variables. You'll notice that I'm not writing x1, x2, and x3. If you like, you can think about x, y, and z as being nicknames for those 3 variables, but that's not necessary because the variable names aren't real anyway, right? Remember that polynomials don't intrinsically refer to any names. They're just assignments of coefficients to tuples of non-negative integers. So I get to choose the names however I like, and it doesn't matter. So we'll call them x, y, z. All right. Now the point I want to make here, and this is something that's going to come back in many guises in the course, is it's not clear how to sketch V. Now this word sketch is hiding a universe of questions, right? You can't... You're probably familiar if you've done, say, a first-year university course in calculus, how to sketch curves. You find local minima and maxima and stuff like that. In more than one variable, it's not so clear you have any go-to methods for getting a rough idea of what this set looks like, right? So how are you supposed to understand a geometric object like that? So this subset of A3, you've got an equation for it, but that doesn't mean you know really much about it. How should you understand this set? Well, there's many tricks and things you can do. One of them is to slice through this surface with lower dimensional object, well, with other objects, including planes, right? So we're going to discuss that briefly now. So one way is to cut it with a plane. And the easiest plane to imagine would be a level set for one of the coordinate functions. Right, so for C in R, set H sub C to be a plane which is just sitting parallel, so to speak, with the xy plane at height z equals c. So that is this set. But of course this is also an affine variety, right? You get this by looking at where the equation z minus c vanishes, right? Because that's the only condition here. Then if we slice through V, so here's V, we don't understand it. Here's HC. Of course, V doesn't look anything like that, but this is more like a three-dimensional question mark than anything, okay? Well, I can look at this here, right? So let V sub C to be V intersect HC. Well, if I look at all the points where F vanishes, and where z minus c vanishes, well, that's just the same as taking both equations at once, right? So that's f z minus c. Now, if you think about it, that's the same as substituting z equals c. And this you should have a bit of a ponder about. I can just make that substitution in capital in f and look at the zero set of this. Now, this is easier to understand, right? Because this is just a curve in two-dimensional space. Yeah, it's not equal to, I guess. Say it like this. Okay. So now let's have a look at what those slices are. So what are these slices? Well, if c is less than 0, we have, rearranging that equation, x squared minus the absolute value of c times y squared is c cubed. And I'm just looking at that thing marked easier over there and setting it equal to 0. And if c is greater than 0, we have, rearranging it like this. I'm doing these rearrangements because I want these things on the right hand side to be positive. I'm going a bit quick here because we've gone over time already, but you can see the details in the notes. The point I want to make is that these are both families of hyperbolae. So this is a hyperbola so it's x squared minus y squared, something times y squared is equal to some positive number. If you put y equal to 0, you'll get two solutions for x. So this is something that looks like this. This is also a hyperbola, but the role of x and y is interchanged, so it looks like that. And if c is equal to 0, well, look at that equation. You just get x squared equals 0. Okay, so the solution set here is just the y-axis. Okay, so here you get these two curves, here you get these two curves, and then when I slice at c equals 0, I just get the y-axis. Okay, now c controls this point of intersection. So as c gets closer to 0, these hyperbolae get closer and closer to the origin until they kind of cross over. Okay, so that's a very rough description. See the notes for more pictures, but we can also just look at the thing itself. Okay, so I encourage you to detach from OrbCam and we'll just go over and discuss the shape sitting over there in three-dimensional space. Okay, so if you don't detach, you won't be able to hear me when we're over there. Okay, so, well, how can we map this family of two families of hyperbolae and the y-axis? So if you rotate your view around this thing a bit, hopefully you'll be able to see that c less than 0 is sort of below that bridge. Can I get up there? Need to get up here to present. Okay, where my head is, this is the origin. Okay, where my microphone icon is. The line the y-axis line, which is slicing. So if you take a plane which is parallel to the ground and slice through the top of my head, that's the plane H0. And the plane H0 intersects this surface in the y-axis. So the y-axis is this line you can see if you rotate your camera that kind of runs through the shape. As you go above my head, you're slicing with a plane which is HC for C positive, and you'll see in that slice a hyperbola, which has the depicted form where it's curving sort of down towards the x-axis. And if you take a slice with HC negative, you'll see a hyperbolas that go in the sort of opposite orientation. Okay, so this surface is made up of these two families of hyperbolae that kind of cross over and turn into each other at the plane H0. Now the reason this is interesting, it's a beautiful surface, but it's interesting because it's singular. You can see if you look around the sides, so to speak, so maybe over here. So if you look towards the shape from my point of view, you'll see the surface cross over itself at some point. Right? And at that point, the surface doesn't look like locally a plane. It's got this funny X configuration that you can kind of see in the picture. And that's a singularity. And that's the kind of object, the kind of phenomena that appears all the time in algebraic varieties, which makes this properly an object of algebraic geometry rather than differential geometry, which is about things that locally never have these points where they cross over themselves.
Is the whole line here where it crosses itself, are all of the points on that line singularities?
That's right, yeah. So the whole y-axis on that plane is a singularity, that's right.
So Ed, to be clear, the y-axis isn't like up and down here. It's like cross. It's like horizontally.
Yeah, that's right.
Yeah, it's parallel with the ground.
Yeah, it's not the Roblox y-axis. It's the Roblox z-axis or something, yeah. Okay. Matt had a question about the notes. Yeah, so if you look at the side onto the surface, you'll see the X, right? And the cross product just means that it goes into the board, so to speak, into the world a bit. So it's like an X, but it has some depth to it. That's all that means. Does that make sense? Okay, so I'll just finish on a bit of a foreshadowing. So we have two ways of thinking about this surface. One is the equation that I gave you. In the notes, there's also given a parameterization, which is what's used to generate this diagram. So I don't generate this diagram just using that equation. Instead, I know how to find points on this surface given two real numbers u and t. So there's a map from some subset of R2 into this surface, which is the parameterization, and I evaluate that map on many different points and put little balls at all the points, and that's where this surface comes from. So there's two ways of looking at this surface, as a parameterized thing or as a affine variety just given by some equation. Both presentations are useful. The parameterization is useful. Well, you can see it here. It's pretty. But there's also more serious uses for parameterizations. The implicit presentation, that is the equation, is useful because it gives you an easy check to see if a point is on the surface or not. You just need to compute this polynomial and it's either 0 or it's not. That's not so clear if you have a parameterization only, how to check if something is on the surface that's parameterized or not. So the interplay of these two ways of describing this single object is quite interesting and leads to two problems. Parameterization, that is, given an affine variety, can you find a parameterization for it? In general, the answer to that is no. And implicitization, which is the question, if you just have the parameterization, can you determine a set of equations which cut out the same thing as your parameterization? And the answer to that is yes, and that's in some sense the final result of this course will be to say that that's true and show you how to do it effectively. Okay, so that's it for course number 1. Thanks everyone.